Water velocity and velocity pressure are two key parameters in the hydraulic calculation of fire sprinkler systems, and understanding their roles provides deeper insight into how sprinkler systems actually perform. In this video, we will explore several advanced topics related to water velocity and examine how considering its effects can help us better understand and potentially optimize the hydraulic demand of a fire sprinkler system. In advanced hydraulic calculations in fire sprinkler systems, one of the most fundamental parameters we encounter is water velocity inside the pipe. In simple terms, velocity describes how fast the water is moving through a pipe. In fluid mechanics, velocity is defined as the volumetric flow rate divided by the cross-sectional area of the pipe. In its most basic form, the relationship is expressed as V equals Q over A. This equation simply tells us that the speed of water depends on two things: how much water is flowing and how large the pipe is. If the flow rate increases while the pipe size remains the same, the velocity increases. Conversely, if the pipe diameter increases while the flow remains constant, the velocity decreases because the same amount of water has more space to move through. In fire protection engineering, we usually work with the gallons per minute for the flow rate and inches for the internal diameter of the pipe. Because of these commonly used units, the velocity equation is often rearranged into a practical form that allows engineers to directly calculate water velocity in feet per second from the flow in gallons per minute and the internal pipe diameter in inches. Understanding velocity is important because it influences several aspects of sprinkler system performance, including friction loss in pipes and, in some cases, the contribution of velocity pressure in hydraulic calculations. In the following sections, we will explore how water velocity interacts with these hydraulic principles and how it affects the accuracy of sprinkler system calculations. When discussing high water velocity in pipes, three concerns are often raised. The first concern is wear and tear of the piping, particularly in plumbing and mechanical systems. At very high velocities, moving water may increase internal erosion of pipes and fittings over time. This can potentially accelerate deterioration of the piping material, especially in steel pipes, and raise questions about the long-term durability of the system. However, this concern does not directly apply to fire protection systems because sprinkler piping does not operate under continuous flow conditions. Fire sprinkler systems are not active on a daily basis, and the piping typically remains static for long periods of time. In addition, the piping in a fire sprinkler system will rarely experience flows close to the calculated hydraulic demand. Even in the uncommon situations when such high-velocity flow does occur, it typically lasts only for a short period during a fire event or system test. Because of this limited duration, the flow is unlikely to have any meaningful effect on the service life of the piping. Therefore, wear and tear resulting from high water velocity is generally not considered a significant concern in the design of fire sprinkler systems. The second concern sometimes mentioned is noise caused by high-velocity flow. As water velocity increases, turbulence within the pipe also increases, particularly at fittings such as elbows, T's, and valves. This turbulence can generate noticeable noise in piping systems. In fire sprinkler systems, however, this issue is generally insignificant. When a sprinkler system activates, the sound of alarms and water gongs, along with the general noise and activity during a fire event, are typically far louder than any noise produced by water flowing through the piping network. As a result, noise generated by high-velocity flow is usually not considered a meaningful concern in the design of fire sprinkler systems. The third concern relates to hydraulic calculations and the accuracy of the Hazen-Williams formula as water velocity increases. Because of this, some people believe that design standards should establish a maximum allowable velocity for applying the Hazen-Williams equation. As we discussed in the previous video on the Darcy-Weisbach equation, we noted that Darcy-Weisbach is the more accurate fundamental equation. We also explored an example comparing the two methods and saw that their results were nearly identical at a flow of 20 gallons per minute in a 1-inch Schedule 40 steel pipe, which corresponds to a velocity of about 7.4 feet per second. Now let's increase the velocity and see how the accuracy of the Hazen-Williams formula changes as the flow rate rises. As shown in this table, I calculated the pressure loss for different water velocities using both the Darcy-Weisbach and the Hazen-Williams equations. All values are based on a water temperature of 68 degrees Fahrenheit, which is equivalent to 20 degrees Celsius. The pipe roughness is taken as 0.004 inches, corresponding to a Hazen-Williams C factor of 120. In this table, the first column shows the nominal pipe size in inches, and the second column lists the actual internal diameter. The third column gives the water velocity in feet per second, and the fourth shows the corresponding flow rate in gallons per minute. Next, we see two columns of pressure loss per foot, one calculated using the Darcy-Weisbach equation and the other using the Hazen-Williams formula. The seventh column shows the difference in pressure loss between the two methods, and the final column expresses that difference as a percentage. The table makes one thing very clear. As water velocity goes up, the Hazen-Williams formula loses accuracy. This brings up two big questions. Is it possible to set a maximum velocity limit for our calculations? And more importantly, does this mathematical error even matter in the real world? To answer the first question, let's look at the tables for other pipe sizes: 1 1/4, 1 1/2, 2, 2 1/2, 3, 3 1/2, 4, and 6 inches. Now, let's assume we are members of the technical committee for NFPA 13 and we want to set a limit for water velocity. Imagine we all agree on 10% as our maximum error margin. Look at what happens in the data. In a 1-inch pipe, we break the 10% threshold at just 30 feet per second. Step up to 1 1/4 and 1 1/2 inch pipes, and we don't cross that line until 40 feet per second. In a 2-inch pipe, it takes a massive 50 feet per second to finally exceed a 10% error. And look at the 4-inch and 6-inch pipes. Even at an extreme 50 feet per second, they only hit an 8% and 5% error. They never cross the threshold. It gets even more interesting when we look at the tables for CPVC pipe. At none of these velocities do we exceed the allowable threshold. This data illustrates why setting a universal velocity limit is impossible. If the code simply said maximum velocity is 30 feet per second, it would successfully protect the 1-inch pipe, but it would completely penalize larger pipe sizes such as 4 or 6 inches. Therefore, NFPA 13 doesn't limit velocity because the exact error threshold changes drastically based on pipe size and material. To actually enforce a limit, they'd have to publish a massive, confusing chart with a different maximum for every single variation. In the end, that would just create headaches for system designers. Now let's go back to the second question and see how this pressure difference plays out in a real project. In our calculations for Schedule 40 pipes, the largest discrepancy between the Darcy-Weisbach and Hazen-Williams equations occurred at a velocity of 50 feet per second, corresponding to about 135 gallons per minute in a 1-inch pipe. First of all, we should remember that 135 gallons per minute is an extremely large flow rate for a 1-inch pipe. In practical terms, that would mean supplying roughly 6 sprinklers through a single 1-inch branch line. Even at this unusually high flow, though, the difference between the two equations is only 1.035 pounds per square inch per foot. This pressure difference is really not a big deal when you consider the accuracy of the water supply data itself. Even under the best conditions, a flow test on a sprinkler system can show pressure fluctuations of around 10 pounds per square inch. Anyone who has ever watched a pressure gauge bounce during a hydrant test knows exactly what that looks like. So when the supply pressure can vary by that much, 1 pound per square inch per foot difference between Darcy-Weisbach and Hazen-Williams becomes almost irrelevant in the context of the entire system. You might be thinking, sure, but if that pipe is 100 feet long, that error multiplies into a massive 103 pounds per square inch difference. Mathematically, that's true, but in the real world, this situation simply cannot occur. If we had a 100-foot section of 1-inch Schedule 40 pipe flowing 135 gallons per minute, the Darcy-Weisbach equation would predict a pressure loss of roughly 548 pounds per square inch over that length. And when we remember that the maximum allowable pressure in most fire sprinkler systems is only 175 pounds per square inch, it becomes clear that such a flow is physically impossible in an actual installation. In other words, the pressure limitations built into the standards naturally cap the flow and velocity long before you ever reach these extreme conditions. The system simply cannot operate at those unrealistic velocities. So the theoretical error between the two equations never has a chance to accumulate over long pipe runs. As a conclusion, we can say that the pressure limitations of the system naturally restrict the velocity. Whenever velocities become high, they are confined to very short sections of pipe, and the system simply cannot sustain those extreme flows over long distances. Because of this, the difference between the Darcy-Weisbach and Hazen-Williams equations never becomes large enough to influence the overall hydraulic calculation in any meaningful way. The two methods produce results that are sufficiently close for practical design, especially when we consider the much larger uncertainties involved in real-world system design. This is why NFPA 13 does not impose a velocity limit and continues to allow the Hazen-Williams formula for sprinkler system design. The mathematical differences exist, but their impact on actual system performance is negligible. Most of the concepts we reviewed in this section come from two excellent articles written by Professor Kenneth Isman, the former Vice President of Engineering at the National Fire Sprinkler Association, and Mr. Roland Huggins, the former Vice President of Engineering and Technical Services at the American Fire Sprinkler Association. If you'd like to explore the topic of water velocity in even greater depth, their articles are extremely valuable resources. In the flow rate and pressure video, we reviewed the different types of pressure acting on water as it moves through a pipe, and we explained that the total pressure is the sum of the normal pressure and the velocity pressure. Regarding the flow discharged from a sprinkler, the important point is this. For a sprinkler located at the end of a line, or anywhere water approaches it from both directions, the total pressure is what determines the discharge, because both the normal pressure and the velocity pressure contribute. However, in all other configurations where water reaches the sprinkler from only one direction, only the normal pressure is responsible for the discharge. In those cases, the velocity pressure does not contribute to the sprinkler's discharge flow. Although we usually ignore the velocity pressure because its value is very small, when we do account for it in advanced hydraulic calculations, we can actually reduce the calculated system demand. To calculate the velocity pressure, we simply use the formula 0.001123 multiplied by the flow rate squared and then divided by the diameter raised to the fourth power. In this formula, the velocity pressure is expressed in pounds per square inch, the flow rate Q is in gallons per minute, and the pipe diameter D is in inches. For example, if the flow is 20 gallons per minute and the internal diameter of the pipe is 1.049 inches, the resulting velocity pressure is about 0.37 pounds per square inch. As we can see, this value is relatively small compared to the total pressure required for sprinkler discharge. However, because velocity pressure is proportional to the square of the flow rate, an increase in flow results in a much larger increase in velocity pressure. For example, at 40 gallons per minute, the velocity pressure is 1.48 pounds per square inch, while at 80 gallons per minute it increases to 5.93 pounds per square inch. When we ignore the velocity pressure in hydraulic calculations, we are effectively assigning all of the pressure to the normal pressure. As a result, the sprinkler appears to have more available pressure than it actually does, which means the calculated discharge will be higher than the true discharge. Although accounting for the velocity pressure in the hydraulic calculation can reduce the system demand, it also makes the calculation more complex. Let's review this in an example. In this figure, 3 standard spray sprinklers with a K factor of 8 are protecting an extra hazard group 2 occupancy. Each sprinkler covers 100 square feet, and based on the required density of 0.4 gallons per minute per square foot, the minimum required flow for each sprinkler is 40 gallons per minute. We start our calculations from sprinkler 101. As we reviewed earlier, since this sprinkler is located at the end of the line, the total pressure is responsible for its discharge. We can simply calculate the required pressure by dividing the flow by the K factor and then squaring the result, which gives us 25 pounds per square inch. Now, using the Hazen-Williams formula, we can calculate the total pressure at node 102. Since for this sprinkler only the normal pressure is responsible for the discharge, we must first determine the velocity pressure and then subtract it from the total pressure to obtain the normal pressure. On the other hand, since the velocity pressure at this node depends on the flow passing through the pipe between nodes 102 and 103, and that flow is the combined discharge of sprinklers 101 and 102, the calculations become a little more complex. To solve this, we start by guessing a flow for sprinkler 102. Based on that guessed flow, we calculate the velocity pressure and then determine the normal pressure. Using this normal pressure, we calculate the actual flow for sprinkler 102. If the calculated flow matches our initial guess, the value is correct. If not, we repeat the process until the flow converges. For the first guess, we can choose any flow. However, let's select a flow of 43.6 gallons per minute, which is calculated based on the total pressure we found at node 102 and the K factor of the sprinkler. Based on this guessed flow, we calculate the velocity pressure in the pipe between nodes 103 and 102 to be 2.16 pounds per square inch. Subtracting this velocity pressure from the total pressure gives us a normal pressure of 27.54 pounds per square inch. Using this normal pressure, the resulting flow for sprinkler 102 is 41.98 gallons per minute. Since this value does not match our initial guess, we repeat the process using the new flow. This second iteration gives a velocity pressure of 2.08 pounds per square inch, a normal pressure of 27.62 pounds per square inch, and a calculated flow of 42.04 gallons per minute. Again, this value does not match the flow used at the beginning of the iteration, so we continue. Using 42.04 gallons per minute for the next step, the velocity pressure remains 2.08 pounds per square inch. The normal pressure becomes 27.62 pounds per square inch, and the calculated flow is again 42.04 gallons per minute. Because the calculated flow now matches the flow used at the start of the iteration, the process has converged. Therefore, the actual flow for sprinkler 102 is 42.04 gallons per minute. We follow the same procedure for sprinkler 103. First, we determine the total pressure at node 103. Then we guess the flow for the sprinkler, calculate the velocity pressure in the pipe between nodes 103 and 1, and perform the iterations to find the actual flow of the sprinkler. If we compare the flow of sprinklers 102 and 103 with and without accounting for the velocity pressure, we see a total reduction of about 5.1 gallons per minute. In a system with more sprinklers in the design area, this reduction can become significant, lowering the overall system demand in both required flow and pressure.